Hello. So, in the last few classes, we have talked about different types of linear discriminators and different types of techniques for designing of linear discriminators. So, we have talked about the statistical model, that is starting from the probability distribution of the samples belonging to different classes. How we can design a classifier using Bayes decision theory. We have also talked about other type of designing techniques for linear discriminators when we have a set of samples which are given for training of the classifier or design of the linear discriminator. And one of them we have discussed is use of perceptron criteria. We have also talked about the relaxation criteria for designing of linear discriminators. We have also talked about the mean square error criteria for designing of linear discriminators. Then various such techniques we have discussed in last few classes. We have also talked about a linear machine, where we have said that every class has a discriminant function, and for a given unknown sample, where when you design the discriminant function, you make use of the samples for which the class belongingness is known. So, effectively what we are trying to do is, we are trying to implement supervised learning technique. That means, training of the classifier is supervised, in the sense the classifiers are trained using some samples for which the classes are known. So, we have also talked about a linear machine, where every class has a discriminant function. So, for a given unknown sample, what we try to do is, we compute the discriminant functional value for that unknown sample for every classes. So, whichever class gives maximum value, the unknown sample is classified to that particular class. So, in today's class, what we will do is, we will take a few problems, and try to solve those problems, so that your idea of designing of such classifiers become more clear. So, let us take the first problem, where we have the discriminant functions for every classes, and from that discriminant functions, from that set of discriminant functions, we have to find out what is the class boundary between different classes, and also what is the region in the feature space which are allotted to different classes. So, we will take the first problem, where I assume that I have got 3 classes. Say the classes are omega 1, omega 2 and omega 3. So, I have got these 3 different classes. For every class, I have a discriminant function. That means, for class omega 1, I have a discriminant function which is given by g 1 of x. For omega 2, I have a discriminant function which is given by g 2 of x, and for omega 3, I have a discriminant function which is given by g 3 of x. So, these are the 3 discriminant functions for 3 different classes. For omega 1, I have g 1 x, for omega 2, I have g 2 x, and for omega 3, I have g 3 x. So, naturally, our classification is, if I find that g 1 x is greater than g 2 x, then x will be classified to class omega 1. If g 3 x is greater than g 1 x and g 3 x is greater than g 2 x, then x will be classified to class omega 3. If g 2 x is greater than g 1 x and g 2 x is greater than g 3 x, then x will be classified to class omega 2. So, now let us see that what are the different functional forms each of these linear discriminating functions have. So, I will put say g1x is equal to, let us say, 10 x1 minus x2 minus 10. g2x, let us take x1 plus 2x2 minus 10, and suppose g3x is equal to x1 minus 2x2 minus 10. So, these are the discriminating functions, linear discriminating functions for different classes. So, in order to classify a sample to class omega 1, what I have to do is, I have to find out what is the value of g1x, what is the value of g2x, and I have to find out what is the value of g3x. If I find that g1x is greater than g2x, then obviously between these two classes x belongs to class omega 1. If also g1x is greater than g3x, then between these two classes x also belongs to class omega 1. So, undoubtedly the unknown feature vector x will be classified to class omega 1. Now, if it so happens that g1x is greater than g2x, but g3x is greater than g1x. So, those are the different such confusing cases. We will see what happens to all these different confusing cases. So, here what I will do is, this is the discriminating function for class omega 1, this is the discriminating function for class omega 2, and this is the discriminating function for class omega 3. Now, what I want to do is, I want to find out what is the decision boundary between pair of classes. So, between g1 omega 1 and omega 2, what is the decision boundary? Between omega 2 and omega 3, what is the decision boundary? And between omega 1 and omega 3, what is the decision boundary? So, for that, what I need to compute is, I need to compute what is g12 of x, and g12 of x will be given by g1x minus g2x, and if this g12x minus g2x, if this is positive or g12x is positive, then obviously x belongs to class omega 1 when I compare between classes omega 1 and omega 2. So, the decision boundary between the classes omega 1 and omega 2 will be given by g12x is equal to 0 or g1x minus g2x, which is equal to 0. Similarly, I find out what is g23x, that is the decision boundary between the class omega 1 and class omega 2. So, I will compute g23x as g2x minus g3x, and I will equate this to 0 to get the decision boundary between class omega 1 and between class omega 3 and class omega 2. Similarly, I will compute what is g of 13x, which is nothing but g1x minus g3x, and by equating this to 0, I get the decision boundary between class omega 1 and class omega 3. Now, let us see that what each of these functions g12x, g23x or g13x, they take using these discriminating functional values g1x, g2x and g3x. So, from here you find that my g12x which is nothing but g1x minus g2x. So, if I compute this g1x minus g2x, that will be 9x1 minus 3x2. So, this is equal to g1x minus g2x, which is equal to 0. If I compute this, then as I said that it will be 9x1 minus 3x2 is equal to 0, and which is nothing but x1 3x1 minus x2 is equal to 0. Similarly, when I compute g23x, which is nothing but g2x minus g3x. So, g23x, which is g2x and this gives g2x minus g3x. So, you find that this x1 term gets cancelled and it simply becomes 4x2 is equal to 0. So, that gives me 4x2 is equal to 0, which is nothing but x2 is equal to 0, and x2 is equal to 0 is nothing but x1 axis. Similarly, when I compute g13x, which is g1x minus g3x. So, when I do that, g1x, which is 10x1 minus x2 minus 10, minus g3x, which is x1 minus 2x2 minus 10. So, when I subtract g3x minus g1x, what I get is 9x1 plus x2. So, this is 9x1. So, this is my g1x minus g3x. I have to equate this to 0, which gives me 9x1 minus x2, that is equal to 0. So, you find that the decision boundaries between the pair of classes, the decision boundary between omega 1 and omega 2 is given by 3x1 minus x2 is equal to 0. The decision boundary between omega 2 and omega 3 is given by x2 is equal to 0, which is nothing but my x1 axis, and g13x, which is the decision boundary between class omega 1 and omega 3, which is given by 9x1 minus x2 equal to 0. So, these are the different decision boundaries. And what we are talking about? We are considering two dimensional feature vectors having components x1 and x2. So, it is a two dimensional space. Now, if I plot all these decision boundaries, let us see what is the kind of situation that we have. The first decision boundary is, so I will put it this way. This is say my x1 axis and this is my x2 axis. Okay. Now, when you come to this one, g12x, that is the decision boundary between class omega 1 and omega 2, which is given by 3x1 minus x2 is equal to 0. So, this decision boundary, if I plot, the decision boundary will look like this. So, I will put it this way. So, suppose here I have 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7 and so on. So, this G12x, which is 3x1 minus x2, that will be somewhere over here. This is G 1 2 of x. Coming to this G 2 3 of x, which is x 2 equal to 0, that is nothing but my x 1 axis. So, this x 1 axis this is G 2 3 of x. That is the decision boundary between the classes omega 2 and omega 3. And coming to the next one, sorry, here I have made a mistake. My discriminating functions G 1 x was 10 x 1 minus x 2 minus 10, G 3 x was x 1 minus 2 x 2 minus 10. So, G 1 3 x, which is G 1 x minus G 3 x, will be 9 x 1 plus x 2, which is equal to 0. So, this is 9 x 1 plus x 2, not minus. Okay. So, if I plot this decision boundary on the same graph, you find that this plot will be something like this. Where this is G of 1 3 x. Now, when it comes to G 1 2 x, we said that if G 1 2 x is greater than 0, then x belongs to class omega 1. If it is less than 0, then x belongs to class omega 2. Similarly, G 2 3 x, if G 2 3 x for a given x is greater than 0, then that x belongs to class omega 2. If it is less than 0, then that x belongs to class omega 3. And similarly, considering this G 1 3 x, if G 1 3 x is greater than 0, then that x belongs to class omega 1. If it is less than 0, then that x belongs to class omega 3. So, let us see that what is the positive side of these different decision boundaries. If I take a point say 1 1 and put that into G 1 2 x. So, over here I have G 1 2 x. If I put x 1 equal to 1, x 2 equal to 1, then G 1 2 x is equal to 2. That means, this point 1 1, which is somewhere over here, is on the positive side of G 1 2 x. So, this G 1 2 x, as it divides this two dimensional space into two half spaces, this side of the space is positive and the other side is negative, which means that when I go for classification, this side of the decision boundary is omega 1 and this side of the decision boundary is omega 2. Similarly, when I consider this G 2 3 x, as G 2 3 x is nothing but x 2. So, whenever x 2 is positive, that side belongs to omega 2. Whenever x 2 is negative, that side belongs to omega 3. So, considering this decision boundary, this side belongs to omega 2, this side belongs to omega 3. Similarly, when you consider this 1 3, G 1 3 x, you find that G13x is nothing but 9x1 plus x2. So, if I set x1 equal to 1, x2 equal to 1, this is nothing but 10, which is positive. So, coming to this G13x, this side of the decision boundary gives me class omega 1 and this side of the decision boundary gives me class omega 3. Now, let us try to combine what we get from these three decision boundaries. So, coming to this one, between omega 1 and omega 2, this side belongs to omega 1. Between omega 3 and omega 1, this side belongs to omega 1. So, you find that so far as this decision boundary is concerned, between class omega 1 and omega 2, this half belongs to class omega 1, and considering omega 1 and omega 3, this half belongs to omega 1. So, finally, the region which will be allocated to class omega 1 is the intersection of these two regions, and which is nothing but this region, which is allocated to class omega 1. Then, when I consider omega 2, you find that between omega 1 and omega 2, this half belongs to class omega 2, and between omega 3 and omega 2, it is this half which belongs to class omega 2. It is upper half omega 2 and omega 3, it is the upper half which belongs to class omega 2. So, G1x tells me that this half goes to omega 2 and G23x tells me that this half goes to omega 2. So, finally, the region which is allotted to omega 2 is nothing but this region. So, this is the region which goes to class omega 2. And coming to omega 3, this G23x tells me that this lower half goes to omega 3 and G13x tells me that it is this half which goes to omega 3, and intersection of these two is nothing but this region. So, this is the region which is going to class omega 3. So, when I have these decision boundaries G13x, G12x and G23x, if I have an unknown feature vector which is lying within this region, obviously, this unknown feature vector will be classified to class omega 1. If I have an unknown feature vector which is in this region, this will be classified to class omega 2. And if I have an unknown feature vector which is here, this unknown feature vector will be classified to class omega 3. So, from this different discriminating functions, when I get the decision boundaries divide the spaces into three different subspaces, where every subspace is allotted to one of the classes. So, this was a very simple case. Now, let us think of a situation that if these discriminating functions themselves are taken as the decision boundaries, or in other words, what I mean to say is, if I take say G12x is equal to 10x1 minus x2 minus 10 is equal to 0. G23x is equal to x1 plus 2x2 minus 10 is equal to 0, and say G13x which is x 1 minus 2 x 2 minus 10, which is equal to 0. If I have a situation something like this, then let us see how the different regions will be allotted to different classes. So, for that what I have to do is, I have to again draw the state lines represented by these three different functions. So, let us draw those state lines. So, I have again this axis, this is x 1, this is x 2. Okay. Here you find that this particular state line 10 x 1 minus x 2 is equal to 0. See, if I put x 1 is equal to 0, x 2 will be equal to minus 10. So, that will be point somewhere, let us say over here. And if I put x 2 is equal to 0, x 1 will be equal to plus 1. So, that will be a point somewhere over here. So, I have this g 1 2 x in this case, which is given by this state line. This is g 1 2 x. Coming to the next one, g 2 3 x. If I put x 1 is equal to 0, x 2 will be equal to 5. Okay. So, 0 5, which will be a point say somewhere over here, and if I put x 2 is equal to 0, x 1 will be equal to 10, that will be a point somewhere over, sorry, if I put x 2 is equal to 0, then x 1 is equal to 10. So, that is a point somewhere over here. Okay. And if I put x 1 is equal to 0, x 2 will be equal to 5. So, that will be a point somewhere over here. So, this is a state line which represents g 2 3 of x. And coming to the third one, which is g 1 3 x, which is nothing but x 1 minus 2 x 2 minus 10 is equal to 0. So, here you find that if I put x 1 is equal to 0, x 2 will be equal to minus 5. So, that will be a point somewhere over here. And if I put x 2 equal to 0, x 1 will be equal to 10. So, that is this point itself. So, I get a straight line which is this, and this straight line represents g 1 3 x. Okay. So, now let us put the point 0 0 on each of these, to each of these discriminating functions. So, for 0 0, you find that g 1 2 x will be is equal to 0, g 2 3 x will also be g 1 2 x will be negative, g 2 3 x will be negative, g 1 3 x that will also be negative. So, that means this origin lies on the negative side of each of these planes. So, as the origin lies on the negative side, that indicates that considering this g 1 to x, this side of g 1 to x is omega 1, because on this side I have g 1 to x is equal to is positive, and on this side it is omega 2. Coming to 1 3 x, as this is on the negative side, so g 1 3 x will be positive on the other side. So, this side will be your omega 1 and this side will represent omega 3. Coming to this g 2 3 x, this side will represent omega 2 and this side will represent omega 3. So, with this, now let us try to distribute or allot different regions to different classes. So, here you find that between class omega 1 and omega 2, this side is omega 1, and between omega 3 and omega 1, this side is omega 1. So, when I take the intersection of this and this, you find that this is the region which will be allotted to class omega 1. Sorry, this is the region that will be allotted to class omega 1. Similarly, coming to omega 3, this side between omega 1 and omega 3, this side is omega 3, and between omega 2 and omega 3. So, coming over here, this side goes to omega 3, and between omega 2 and omega 3, this side goes to omega 3. Okay. So, I will have this particular region which will be allotted to omega 3. And coming to omega 2, you find that this is the region which is allotted to omega 2, and between omega 2 and omega 3, this is the region on this side that is allocated to omega 2. So, if I take the intersection, then this is the region which will be allocated to omega 2. So, I have this region allotted to omega 1, I have this region allotted to omega 2, and I have this region allotted to omega 3. And as I do that, you find that there is a region over here and there is a region over here. These two regions cannot be allotted to any of the classes. So, I have some empty region, or these are called ambiguous regions. So, when I have this linear discriminator, considering the decision boundaries between different classes, and if I have a multi-class problem, it is quite possible that in the feature space I can have few subspaces in which if a feature vector falls, that feature vector cannot be classified to any of the classes, because those subspaces are actually ambiguous regions. So, this is one of the problem that I wanted to discuss, to see that how you can solve or how you can identify the regions belonging to different classes when you have linear discriminating functions. Okay. So, the second problem that I will try to discuss today is on classifier design using perceptron criteria. So, if you remember, what we said is, in case of perceptron criteria, the criteria function for designing of the classifier was something like this: J p of say W, which was given by minus W transpose Y, where this summation is taken over all Y which are misclassified. Okay. And to get the value of W that minimizes this criteria function, the perceptron criteria function, we have used the gradient descent procedure. And the gradient descent procedure was something like this, that initially you assume or you set an weight vector which is set at random. So, initially you assume an weight vector W naught, and then in every iterative step you set say W k plus 1 in the kth iteration, which comes from W k, that is your weight vector at the previous iteration, and we are following gradient descent approach. So, it will be minus eta times grad of J P W, where J P W is given like this. And if I take gradient of J P W, which will be nothing but minus summation of y for all the samples y which are misclassified. So, effectively this algorithm comes to W k plus eta times sum of y for all y which are misclassified. And how do I get this y? If my original given feature vector is x, I append 1 to this x. So, if this x is say x 1, x 2 up to x d, I get y by appending 1 to this vector. So, my y becomes 1 x 1 x 2 up to x d. And then what we do is, if this y belongs to class say omega 1, y remains as it is, but if y belongs to class omega 2, then we negate y. So that whenever a sample is correctly classified, this term is always positive. W transpose y is always positive if the sample is correctly classified. Whereas, if the sample is not correctly classified, then W transpose y will be negative, making this minus W transpose y to be positive. Okay. And these are the iterative steps which have to be performed unless the algorithm converges. That means, unless I get a W weight vector which classifies all the training samples correctly. So, this was our perceptron criteria for design of linear classifiers, and this is particularly the one which is applicable for a 2-class problem. So, we are considering a 2-class problem. Then we have extended this concept to a multi-class problem by using a construction technique which is called Kessler's construction. So, I will consider a 2-class problem. I will take a problem from a 2-class case and try to see the different steps of the algorithm, how your vector W evolves. Of course, I will not try to solve the entire problem, I will not try to get the solution, but I will simply explain the steps. The reason is it takes a large number of iterations. Okay. So, I get a situation something like this. Suppose you have been given a set of feature vectors, say 1, 8, 2-dimensional feature vectors, then 6, 7, then 8, 5, then 11, 4. So, this is the set of feature vectors which are taken from class omega 1. And I have another set of feature vectors, say 2, 4, maybe say 3, 3, maybe 6, 2, and suppose 11, 1. These are the feature vectors which are taken from class omega 2. So, I have this 2 sets of feature vectors which are my training vectors to train the classifier. So, it is a supervised learning. And I also assume that initial weight vector, which we said that the initial weight vector is taken at random. So, I assume that my initial weight vector W 0 is something like say minus 10, 1, 1. So, this is my initial weight vector. So, considering these vectors to be the vectors x, now I have to compute y out of these vectors. Okay. So, as we said that we have to append 1 to each of these vectors, and after appending 1, all the vectors which are coming from class omega 2, they have to be negated. So, I will get y 1 I will put it like this, I will get y 1, which is nothing but 1 1 8, because I have to append an 1 over here. So, it becomes 1 1 8, y 2 is 6 7. So, I will get 1 6 7, y 3 is 8 5. So, y 3 will be 1 8 5, y 4 is 11 4. So, I will have y 4, which is 1 11 4. So, these are the appended samples or modified samples from class omega 1. In the same manner, I have to get the appended samples or modified samples from class omega 2. So, I will take these samples from class omega 2, and as we have said that after appending 1, these vectors are to be negated. So, my y 4 or y 5 will be, this is 2 3. So, I will have 1 2 3 and this is 2 4. So, I will have 1 2 4 and then I have to negate it. So, it will be minus 1 minus 2 minus 4. So, y 5 will be minus 1 minus 2 minus 4. In the same manner, y 6, x 6 is 3 3. So, y 6 will be minus 1 minus 3 minus 3, y 7 which is 6 2. So, y 7 will be minus 1 minus 6 minus 2, y 8, x 8 was 11 1. So, y 8 will be minus 1 minus 11 minus 1. So, these are all my modified samples. And I also take where this, if you look at this algorithm, this eta which indicates the rate of convergence. Let me take this rate of convergence eta is equal to say 0.2, and as I said my initial weight vector w 0 which is minus 10 1 1. So, how the algorithm has to work. I have to take w transpose y 1 for each of these y 1s. Then for the y 1 for each of these y's, then for that sample y, if w transpose y is positive, that sample is correctly classified by this weight vector. If w transpose y is negative for any of the y, then that sample y is misclassified by this weight vector. So, I have to identify all those samples y which are misclassified, for which w transpose y is less than 0. So, all those are misclassified samples, and those misclassified samples are to be used in my gradient descent procedure for modification of the weight vector w. So, let us see what values of w transpose y that I get for different samples y. So, if I take, as you find that y 1 1, the first component is 1, second component is 2, third component is 8. So, clearly here it is w 0 at the 0th iteration, that is the initial value. Okay. So, w 0 transpose y 1 which will be minus 10 plus 1 plus 8, okay, which is nothing but minus 10 plus 1 plus 8, which is nothing but minus 1, that is negative. That means, y 1 is misclassified by this w 0. Coming to y 2, the w transpose y becomes minus 10 plus 6 plus 7, which is nothing but 3, that is greater than 0. So, w 2 is correctly classified by this sample. So, I do not have to consider w 2 for modification of w, but I definitely have to consider y 1 for modification of w. So, let us see that what these different values that we get. I will get w 0 transpose if I compute this W 0 transpose y 1, which as I said that this has a value minus 1, which is less than 0. So, I have to consider y 1 for modification of my weight vector. When I consider W 0 transpose y 2, W 0 transpose y 2 is plus 3 as we have just seen, which is greater than 0. So, I do not consider y 2 for modification of the weight vector. Similarly, W 0 transpose y 3, which also be plus 3 greater than 0, I do not have to consider y 3 for modification. W 0 transpose y 4, which is it will come out to be plus 5, that is again greater than 0. W 0 transpose y 5, which will be 4 if I compute this, which will again be greater than 0. W 0 transpose y 6, which will again be plus 4 greater than 0. W 0 transpose y 7, which if you compute, it will be 4 again, which is greater than 0. W 0 transpose y 8, if you compute this, this will be minus 2, which is less than 0. That means, I have to consider this y 8 for modification of the weight vector W. Now, looking at this algorithm, you find that weight updation algorithm is W k plus eta times sum of y, where y's are misclassified. So, here over here it is y 1 and y 8 which are misclassified. So, sum of y of the misclassified samples is nothing but y 1 plus y 8. And you look at this or modified samples, y 1 is 1 1 8 and y 8 is minus 1 minus 11 minus 1. So, if I add these two, what I get is 0 minus 10 7. So, the sum of y is nothing but 0 minus 10 and 7. This is sum of y, which are misclassified. So, now what I have to compute is, by using this, I have to compute the next iterated value of W, which is equal to W 1, because I had W 0, I had chosen W 0 at random. So, my W 1 becomes W 0 plus eta times sum of y for misclassified samples, where eta is, we have assumed eta to be 0.2. So, this W 1 simply becomes, what was my W 0? W 0 was, if you look at here, it was minus 10, 1, 1 plus eta is 0.2 times sum of y, which is 0 minus 10 7. So, eta times sum of y will be 0 minus 10 into 0.2, that is minus 0.2, and 7 into 0.2, which is 1.4. Right. So, W 1 simply becomes minus 10 minus 1 and 2.4. So, you see that how we have modified the weight vector W from W 0 to W 1. Using W0, I have identified all the feature vectors, all the samples y which are misclassified. Those misclassified samples are used to modify W0 to get W1. Now, as I have this W1 now, I have to try to classify all those samples y1 to y8 using this W1. So, I have to compute W1 transpose y1, I have to compute W1 transpose y2, W1 transpose y3 up to W1 transpose y8. And I have to identify all those y's for which W1 transpose y is negative. And these are the samples, these are the y's which will be used to update W to get W2. So, if I compute this, you will find that W1 transpose y1, that will be 8.2, which is positive. W1 transpose y2, which will be 0.8, which is also positive. W1 transpose y3, that will be minus 6, which is negative. That means, this y3 has to be used for modification of W. Similarly, W1 transpose y4, if I compute, it will be minus 11.4, which is again negative. So, y4 has to be considered for weight updation at the next iteration. W1 transpose y5, which will be equal to 2.4, that is greater than 0. W1 transpose y6, which will be 5.8, again greater than 0. W1 transpose y7 will be 11.2, again greater than 0. W1 transpose y8, which will be 18.6, again greater than 0. So, I have to consider this y3 and y4 to get my W2, that is the weight vector to be used at the next iteration. And if I add this y3 and y4, so sum of y is nothing but y3 plus y4, and you find that y3 is this 185 and y4 is 111.4. If I add these two, I get 2, 19 and 9. So, that will be equal to 2, 19 and 9. So, W2 that I have, that is the weight vector to be used at the next level of iteration, is nothing but W1 plus eta times sum of y, or y3 plus y4. So, I had W1, that is this, that is minus 10 minus 1 2.4. So, from here I get W2, which will be equal to minus 10 minus 1 minus plus 2.4 plus eta times this, and as eta is equal to 0.2. So, I will just have plus 2 into 0.2, that is 0.4, 19 into 0.2, that is 3.8, 9 into 0.2, that is 0.8. So, which will be simply minus 9.6 minus 2.8, and this is 3.2. So, I get my next weight vector W2, which is given by this, that is minus 9.6 minus 2.8 and 3.2. Again, using this W2, I have to try to see whether the feature vectors are correctly classified or not. If with this W2 all the feature vectors are correctly classified, that means W2 transpose y is greater than 0 for all the y, that means this weight vector W2 is my correct classifier. Again, if I get any y which is negative, for which W transpose y is negative, those y's, those feature vectors are to be used at the next step to get the value of W3. And this is how the perceptron criteria works. Then we have also talked about the sequential version of the perceptron criteria. So, in the original form what we are doing is, in every pass I am identifying all the feature vectors which are misclassified by that weight vector, and all those feature vectors are added together, and that is used for modification of the weight vector. In the serial version of the perceptron criteria algorithm, of the perceptron algorithm, I do not identify all the feature vectors. What I do is, the moment I find that this W1 misclassifies Y3, I do not wait for W4 to be identified. Immediately I use this Y3 to get W2, which will be W3 plus eta times Y3. So, immediately I get, sorry, this was W2 is equal to W1 plus eta times Y3, and maybe this W2 will correctly classify Y4. So, Y4 will not be misclassified by this, but it may so happen that for Y7 I find that this feature vector W2 misclassifies Y7. So, whenever it misclassifies Y7, immediately I will compute W3 to be W2 plus eta times Y7. So, whenever I get a misclassified sample, immediately using that misclassified sample, you modify the weight vector. And in a complete pass, if I have a W where for the same W Y1 to Y8 all of them are correctly classified, I will take that W to be my solution vector. Okay. So, I hope with these problems your concept of the discriminating functions, the decision boundaries, the class regions, and the second one have been able to clarify how the perceptron algorithm works to get the weight vector while supervised learning of a classifier. Thank you.